Let's begin by taking a look at some examples of categorical variables. There are many examples in sports, such as in basketball is a shot made or missed. In baseball is a pitch hit or missed. And in football in particular, we're going to be very interested in one type of categorical variable that summarizes a field goal. Is the field goal made or is it missed? Now, categorical variables are very prevalent in medical applications. In particular, is someone infected with a disease like the flu or coronavirus? Yes or no? Those are some examples of a categorical variable with two levels. Categorical variables can have many more levels, such as criminal offense conviction, highest attained education level, food that is eaten for breakfast, and annual income. Now, with respect to the highest attained education level and annual income, notice those are essentially ordinal categorical variables. So in some kind of data analysis involving those, ideally you would like to be able to take advantage of that. And we'll look at how to do that in this course. Also, if you notice with the annual income variable, that was probably measured on a continuous scale, you could say, to begin with, and then essentially put into categories. There are many times where this kind of a way of measurement is actually used. And so what you can see with all these examples is that essentially we live in a categorical world. We like to put stuff into categories so that we can make better sense of it. That's why taking a course on categorical data analysis is so important. Now, in chapters 1 and 2 of my corresponding book and in these notes, we're going to be focusing on these kinds of categorical variables that have a binary outcome, meaning two levels. And you could say that we have binary response categorical variables that we're going to be looking at. Now in section 1.1, we're going to be focusing on estimating the overall probability of success for items in a particular population. These two binary outcomes that we are going to be working with, we're going to generically call them success or failure. And again, we're going to be focusing on the probability of success. This is going to be considered, let's say, a homogeneous population. So every item in the population is going to have, let's say, the same characteristics associated with it. So because of that, then we can then say that we're also looking at the overall prevalence of successes in the population as well. In chapter 2, we will look, in section 1.2, we will be looking at a situation where now we're not necessarily in a homogeneous population anymore. There could be, let's say, some kind of independent variable, explanatory variable, or some factor that could affect the probability of success. And then in chapter 2, we're going to extend this to a situation where there are potentially multiple explanatory variables that could affect the probability of success. So to begin here, let's define some notation. We're going to let y be our binary response variable, where y could denote field goal result, for example, or disease infection outcome. And y is going to be equal to a 1 for success. Y is going to be equal to 0 for failure. We are again interested in the probability of success, so the probability y is equal to 1, and we're going to symbolically denote this as the Greek letter pi. Now in this kind of a situation, we can look at a probability distribution that helps us to model these successes and failures. And as all of you have seen in an introductory stat course before, the probability distribution that's most often used in this particular situation is what's called a Bernoulli distribution. In particular, the Bernoulli probability mass function looks like this. The probability that our random variable y is equal to a particular outcome, that's what we denote by little y. Little y can be 0 or 1, is equal to pi raised to the y power. times 1 minus pi raised to the 1 minus y power. So notice if y is equal to 1, what happens? This part disappears and we're just left with pi. Of course, though, if y is equal to 0, this part disappears and we're left with 1 minus pi raised to the 1 minus y power. So if you notice here with my notation, I'm using uppercase y's and lowercase y's. This is a formal notation that people use in statistics where the uppercase y represents the random variable. I can find probabilities associated with that. And the lowercase y represents possible observed outcomes of that particular random variable. Now there's going to be situations where we're going to be able to, let's say, take a random sample from a population, and we might be interested in, for the first item from that population, what is y for that? Let's call it y sub 1. What is the corresponding outcome for the second item in that population that we obtained from the sample? We'll call that y2. And we could have, let's say, a random sample of size n, so we have n different of these y's. Now, when that happens and each of these y's are independent and they each have the same probability of success, now we can start talking about a binomial probability distribution, where if we look at the sum of all those y's, we're going to denote that sum as w, and w has a binomial probability distribution. Again, coming into this particular course, I expect you've all seen the binomial before, but it's good to review it a little bit here. This is what the binomial probability mass function looks like, where at the very beginning here we have n choose w. In other words, how many different ways can I have w successes, where again w is the sum of these y's. How many ways can I have w successes out of n different trials? And now we have pi raised to the w power, in other words, pi raised to the number of successes power, and we have 1 minus pi raised to the n minus w power, in other words, 1 minus pi raised to the number of failures power. And so what this probability mass function gives us is a convenient way that we can find probabilities associated with having, let's say, maybe 0 successes, 1 success, 2 successes, and so on. So a question that I often like to ask then at the beginning of any statistics course is, well, why are we even looking at probability distributions? You know, why do we have this formal mechanism here to look at probabilities? Well, these probability distributions help us to model real life events, such as the number of people who become infected with a virus, or the number of successes out of how many field goals that were attempted. So it provides us a way to model it, to better understand it. Now, of course, there are certain mathematical assumptions associated with any kind of probability distribution, and rarely will all these assumptions will be actually satisfied. But very, very often, these assumptions will be close enough, you could say, so that we can work with that probability distribution. So let's put this now into context of this field goal kicking example that we saw before. Now, since we will be talking about field goal kicking in a number of examples in this course, I think it's good for us now to, let's take a short look of a video of a field goal. Because I understand not necessarily everyone's as big of a football fan as I am. And so let's make sure that we all understand what a field goal is so that we can talk about it in more detail as we move along. Okay, so let me go ahead and get my video up here. Hold on, it's actually on a different monitor window here.
This is for an NFL record.
Okay, so to set the stage here, this is a field goal that takes place in the National Football League, which is the biggest professional football league out there. And there are two teams being played here, Baltimore and Detroit. The game is actually at Detroit. The game only has a few seconds left. Baltimore's down by 1 point. And so what they're about to do, Baltimore, is they're going to have their field goal kicker, Justin Tucker, attempt a field goal. And this isn't just an ordinary field goal. It's a very, very long field goal. In fact, at this particular time point, it would actually set a record for how long the field goal is if the field goal is successful. Now, a successful field goal gives the kicking team 3 points, 0 points for an unsuccessful field goal. And so if this field goal is successful, the score will change from 16 to 17 to 19 to 17, and now Baltimore wins. If the field goal is not successful, Baltimore loses. So let's go to the video and find out what happens.
66 yards.
So let me pause it here for a second. So Justin Tucker is, if you can see where my mouse pointer is right here, and he's called a field goal kicker, and he's going to try to kick a football from right about here where my mouse is. And his goal is to get the football between these two yellow bars, which are called uprights. And unfortunately, with his camera angle, you can't see it. He also has to get it above what's called a crossbar, which is about 10 feet off the ground. And so if he does that, the field goal is a success, and his team gets 3 points and they win the game. If he doesn't, the field goal is a failure and his team loses the game. Let's again see what happens.
On its way. It bounces off the crossbar, and it's good.
Oh my goodness!
Oh my goodness!
Oh my! Did that just happen?
Yes, it did just happen. So the ball actually bounced off the crossbar and still then made it through this, you could say, goal, and his team won the game. So also in this video, I have a little bit of a different angle so that you can see this kick a little bit better.
Lions.
So there's Tucker kicking that ball, and you can see how it does eventually go through the uprights and above the crossbar. Okay, so a real quick example of what a field goal is. So in our particular situation, let's suppose that a field goal kicker kicks 5 field goals during a football game. Each again can be a success or a failure, and we're going to also assume that all these field goals are attempted under similar circumstances. Now, if you're a football fan, you know that one thing that's very important with respect to a field goal is how far is that field goal kicker from the uprights in that crossbar. How far are they away from that? And so we're going to assume that, let's say, all these kicks are done from the same distance. And again, we have other similar circumstances as well, such as the weather and so on. So now, in order for us to use a binomial distribution and for it to be for it to well approximate what's occurring with a particular situation, we need essentially 5 characteristics to be satisfied. First of all, we have n identical trials. So we have, let's say, in this particular case, 5 field goals that are being attempted under similar circumstances. We have 2 possible outcomes for each trial. In this particular case, a field goal can be a success or it can be a failure, or made versus missed. The trials are independent of one another, meaning what happens on that first field goal is not going to affect success or failure on the second field goal. This might be one of the biggest assumptions dealing with it, because you can imagine a situation where a field goal kicker misses a kick, and then when they come back and do the second kick or the next kick, maybe they're kind of down on themselves, and that might affect their what happens. And so let's just assume, though, that each of these field goals attempted are independent of one another. We also have a constant probability of success for every field goal, again, because we have similar circumstances or that these field goals are being taken on. We can say, sure, that works. And then we're going to let W be the number of successful field goals. It can be 0, 1, 2, 3, 4, 5. So while there's 5 different, let's say, trials or 5 different field goals that are being attempted, there are actually 6 possible outcomes of what can happen because we have that 0 to worry about. So with that, then we can then use the binomial distribution. Now, what you've also seen in another class is that we can think about, like on average, what would we expect the number of field goals made to be? We can also talk about the variability in our random variable that measures the number of field goals that are made. And so, in other words, we can talk about the mean and the variance. So the mean, in other words, what I expect W to be, is n times pi. What that again just says is that, let's say, if I were to go out and kick 5 field goals, calculate the number of successes, or record the number of successes, go out and kick 5 more field goals, go out and record the number of successes. Suppose I did this essentially an infinite amount of times. What on average would be the number of field goals that would be made? Well, it would be n times pi. What measures in the variability of from one time that I'm kicking 5 field goals to another? That's the variance of W. That would be n times pi times 1 minus pi. These particular values can be derived in a mathematical sense. You would see this in a mathematical statistics course. This particular course is meant to be much more on the applied side. So for this and many other circumstances, we're going to take the result for what it is and not actually go through a formal derivation. Okay, so let's put this binomial PMF, probability mass function, to use to calculate some probabilities. Let's say the probability success on each field goal attempted is 0.6, so pi is 0.6. Again, we have those 5 field goals. So here's my binomial PMF, and let's say I want to calculate what's the probability that all the field goals are missed. So the probability W is equal to 0. Excuse me. And so I put in n. I put in 5 for n. I put in 0 for W. I do that everywhere. So notice I have 0.6 raised to the 0 power. 0.6 again is my pi. If I go through all the calculations, I get 0.0102. So what this is saying is it's very unlikely to miss all field goals if you attempt 5 of them and the probability of success on each is 0.6. And hopefully that makes some intuitive sense there. Now we can keep on doing all these calculations for all possible values of W itself. And so we can see, for example, the probability W is equal to 3, or 3 successes out of 5 attempts or trials is about 0.35. How many field goals would I expect to make on average? 3. That's my expected value of W. Doesn't mean I'm going to make 3 every time. It just says if I were to go repeat kicking 5 field goals multiple times, on average, it should be about 3. My variance of W is 1.2. Okay, so let's take a look at how we can do some of these calculations now in R. Now, if you have no R experience up to this point, you should take a look at my Appendix A of my book and the corresponding videos with it. I shouldn't say you should, I say you do need to do that. Now, at the beginning of this particular course, I'm going to take things slow in my actual notes here relative to R, but I will then eventually start picking things up. For those of you who have lots of experience with R, please be patient here. Perhaps you can also learn some stuff that maybe you didn't necessarily know before about how to use R. Okay, so I'm going to come over here to my editor that I'm using for R. I use the TinR editor to do all my R calculations. And so in this particular editor, the first thing that we're going to do is find the probability W is equal to 1. So what's the probability of 1 success? With 5 trials and probability of success on each trial 0.6. So n's 5, pi is 0.6. And there's a function R that does that. That does the calculation automatically for us. And it's called dbinom. D stands for distribution. Binom stands for binomial. Now, inside this function, we have a number of arguments, and we have to specify their corresponding values. These arguments are not necessarily set up corresponding to the notation I use in my book. So for example, the first argument here is called x. This represents the number of successes, what we call w. So I say x is equal to 1. Size corresponds to our n. Prob corresponds to our 0.6, or our probability of success on each trial. So if I highlight that code, I come up here to tin-r to the R send button. What that's going to do is go to my R console window, transfer my code there, do the calculation, and it's 0.0768. Now note that I already had R open to begin with to do these, to work with this R program, and so the way that I actually open it up was I use the R icon here, if you see where my mouse is. Also, something I should mention that I failed to mention before. Let me come back here to my notes. So at the very beginning of my example, this is the format that I use for all my examples. I will say example, and then I have a name for the example that I use throughout my notes. So very often I will come back to this, maybe like a same data set over and over again, and I have a consistent name for that particular example whenever I'm using that data. And then in parentheses, I'll have then corresponding files that are associated with this example. In particular, in this particular case, I have a program called binomial.r. If there was a data set that's associated with it, such as, let's say, data, maybe it's a comma delimited file, so .csv extension, I would put that in that parenthesis as well. And you can download these programs, you can download these data sets then from my corresponding website. Okay, let me come back here. Let me get back to my program. Okay. So I calculated the probability that w is equal to 1. Now we can do the calculations for the entire possible set of w's as well. Again, I can use dbinom. And then for the x argument, instead of just putting 1 there, I can put 0:5. And what that simply tells R is that, okay, instead of just one value, let's do 0, 1, 2, 3, 4, 5. Size equal 5, prob equal 0.6. Come up to my R send button, click on that, it sends it to my R console window, and now here's all the probabilities that we've seen before. So for example, the probability w is equal to 3 is 0.34560. Now we can more, let's say, nicely organize this, more nicely print this off by putting all this information to a table-like format called a data frame. So to do that, I'm going to now take the results that I had before from dbinom, and I'm going to put them into an object called PMF. So PMF less than dash, which is verbalized as the word gets. PMF gets the results from dbinom. Let's go ahead and do that. And if I were to type PMF, of course I get what we've seen before. And then I'm going to create a data frame using the data.frame function. It's going to have two different columns to it, or you could call it two different variables. The first one's going to be called w, which has my values of 0 to 5. My second one is going to be prob, corresponding to the probability mass function values, where I'm going to take those probability mass function values and round them first to 4 decimal places. So there you can see it. So I'm going to put this data frame into an object called save, and then simply print it off. So let me go ahead and highlight that code, run it, and now we have a nice little table display of all these corresponding probabilities. Okay, now we can actually plot these probabilities. So we can see all this stuff in a graphical manner, and I'll show you the code in a second, but this is our goal here. We want to produce this particular plot. So you see on the y-axis we have the probabilities, the probability that my random variable w is equal to one particular value of w. On the x-axis we have those one particular values of w. And notice how high these bars go up, or the height of these bars. These heights correspond to the probabilities. So again, what we've seen before is the probability that W is equal to 3 is 0.34, I believe it was 0.3456. And that's the height of that bar. So let's see how we actually create this plot in R. While I don't need to do this first part, I'm going to do it just to demonstrate it, and also there are some advantages to it. I'm going to open up a graphics window to put my plot into. And the way I do that is use a function called dev or dev dot new, device new. Open up a graphics window. Where the advantage of me doing this is I can control the width. It's going to be 6 inches. Height's going to be 6 inches. The font size, or what they call point size, is going to be a size 12 font. So let me go ahead and do that. And then what happens on a different monitor that I'm using right now, the graphics window opens. And so to actually put something in there then, my plot of interest, I can use my function called plot. Where on the x-axis, I'm going to take the W variable out of save. So if I do save $W just to show you what happens, there's my W variable. So again, remember what you would see in that Appendix A is that to access parts of a data frame, you use the $, and you put the variable name right after it. So the data frame name, $, variable name. My y-axis is going to be those probabilities that we saw. So let me just highlight that and show you. Now the type of plot that I want to do. The H there for that argument name corresponds to height. I'm going to draw these probabilities essentially from 0 on up to their height. That's in the prob variable. I'm going to have an x-axis label of W, a y-axis label of probability of big W is equal to little w. I'm going to put a nice title on the plot. And to put some nice grid lines on the plot, I'm going to do panel.first, meaning first before you do any kind of plotting in that plotting window. Let's put put some grid lines on it. The color of these grid lines is going to be gray. The line type of these grid lines is going to be dotted. And then lastly, how big do I want what's actually the main thing that's being plotted? How big do I want it to be in terms of those lines? So LWD stands for line width. It's going to be 3. And lastly, I'm going to use the AB line function that simply allows me to draw a straight line on a plot that's going to be horizontal at 0. So it's going to be give me a is going to give me a line on the corresponding to the y-axis at 0. So let me go ahead and run that code, and we can see then the result. And here's the plot that you see in the notes. Okay. Now you might be thinking right now, like, wow, this is a lot of code. But especially for those of you who are new to using R, think of my code as a template. You copy this code, let's say, into your own program, and you make changes to it corresponding to the problem of interest. So for example, perhaps instead of having a number of trials or an n of 5, maybe I ask you to use 10. Well, wherever you see 5, change it to 10. Suppose instead of having a pi value, probability success value of 0.6, suppose instead it's 0.2. So wherever you see 0.6, change it to 0.2. So if you think of this as a template, then this is how you start learning what the R code is doing. And eventually you'll get to a point where you're much more comfortable with it, and maybe you don't necessarily need to use my code as a template anymore. Okay, so let's take a look at another example. What I want to do is actually simulate what observations look like if we have a binomial distribution that can be used to characterize a particular situation. So in other words, if I want to simulate, how many successes would I get out of 5 trials if one were to go out and kick 5 field goals? And then maybe how about we simulate another situation where I have 5 field goals? How many successes would I have? And so the reason why we want to do something like this is that many statistical procedures are based upon or rely on these probability distributions. And so if you understand better what these probability distributions represent by simulating what a sample will look like, that helps you understand that probability distribution better. Also, as we will see shortly in our course, this will allow us to use, we will be able to use simulation to evaluate how good a statistical method actually performs. It's a very important thing actually in any kind of class, and through the use of simulation, we can then make that evaluation so that we can decide, well, should I use this statistical method or that statistical method for a particular situation? Okay, so to simulate observations that can be characterized as coming from a population that, or to simulate observations that can be come from a particular population that can be characterized by binomial distribution, we can use a function called R-binom. R stands for random and binom stands for binomial. So let me come back over here to my program again. And if I run this particular code here, R-binom, and that actually let me run just an easier set of code first. I can use the R-binom function. The first argument here is n. That is not Rn that we saw in our notation in terms of the number of trials, like the 5 field goals. Rather, it says, well, how many times do you want to observe these 5 trials? Let's say I want to observe it 10 times. How many trials do I have? Again, we have the size argument. I have 5 there. Prob again corresponds to our pi. So if I run that code, I get this. And so what we see here is that I first observed 2 successes out of 5 trials. Then if I go out and do it again, I observe 2 successes out of 5 trials again. Then the next time was 4 successes out of 5 trials, and so on. And so what this helps me see is, again, what does a sample look like in a situation where a binomial distribution can be helped characterize a population. Now if I were to go and run that code again, let's see what happens. Notice I don't get exactly the same thing. If I do it again, I don't get the same thing. If I do it again, I don't get the same thing. And the reason being is because this is essentially randomly generating this sample, this R-binom function. Now, in terms of for teaching purposes, I like to be able to replicate, get the same sample over and over again. And so whenever you want to do that, not necessarily always for teaching purposes, you can do what's called set a seed. And so the set.seed function, and then in parentheses, some numbers that you choose, tells R basically a place where to start in its algorithm to simulate these values. And every time that you set your seed to a particular number and then subsequently run the R-binom function, you will get exactly the same results, making your results you can replicate it. So let's go ahead and try this. So I'm going to set my seed, and then I'm going to use R-binom again. This time I'm going to use 1,000 different, let's say, observations for having 5 trials. I'm going to put the results into an object called bin5, and then using the head function, I'm going to look at the first 6 of these observations. So let me go ahead and run that code. And here we have it. So the first time I ran the code, the first time I simulated a sample, or simulated the 5 trials, I should say, I got 3 for my observed value. The next time 2, the next time 4. Now if I were to run this exact same code again, I replicate it. I get exactly the same thing back. Okay. Now, this head function is something I use a lot. It's just a quick way to look at, let's say, the first few values in like a data set, or in this case, what R would refer to as a vector. There are other ways to look at the first few observations. So, for example, I could say bin5 and then in using square brackets 1:10, meaning I want to look at observations essentially 1, 2, 3, all the way up to 10. And here we go. So while you would see this in the Appendix A, it's good just as a kind of a reminder here. Notice this leading 1 here. What that basically says is that the first value is 3. Now, if I were to have, let's say, more than, we'll do 100 here. You can see that the first value is 3, the 38th value is 2, the 75th value is 4. Okay. So this bin 5 contains 1,000 simulated values in the situation where we have 5 trials. Probability of success on each trial 0.6. So what on average then are all these W values that we're getting out? What's the average value for all those 1,000 of them? And so what I could do is I could use the mean function to find that out. I get 2.99. Now, that should be what we kind of expected. Because if I go back to where we were before, we said, what would I expect W to be on average if I repeated something essentially an infinite number of times with n equal 5, pi equal 0.6? I would get 3. And what this Monte Carlo simulation then allows us to do is basically see, well, I can't do something an infinite number of times, but I can do it a very large number of times. What would happen? And I get just about what the expected value of W should be. I can also look at the variance of all those 1,000 values. I get 1.23. In other words, what's the variance of all these 0s, 1s, 2s, 3s, all the way up to 5? Just to find the sample variance of that, I get 1.23. And again, what we saw previously in the notes, the variance of W, the true value, if I would repeat this stuff an infinite number of times, is 1.25. So something very close. I can do a histogram of all these these number of successes that I observed, these 1,000 of them. And so to do that, I can open up a new graphics window if I wanted to. I'm just going to use the same one that I just did. And I'm going to use a function called hist. And for the x argument, I put in my data, my sample, put a nice main title to the plot. Probability equal true is just an argument that basically rescales the y-axis so that essentially the relative frequencies, in other words, you could say like the estimated probabilities of observing 0, the estimated probabilities of observing 1 is actually produced on the y-axis. In other words, maybe I should just said it this way. How many times do you observe 0 out of these 1,000? How many times do you observe 1 out of these 1,000? Let's find the sample proportion of those. And then I put a nice y-axis label, and this is what I get. Let me bring up my plot again. And so we can see the height of these bars doesn't quite match up to what we had before. And that's because, unfortunately, because with the discreteness of these W values, the x-axis actually gets screwed up a little bit. And so what I'm going to do is specify instead, I want my, let's say, my breaks in terms of where the categories are on the x-axis to be negative 0.5 to 5.5 by 1. Then if I do that, and also col equal NA means don't color in the bars, it's not necessary. This is what I get. And now we can see something very similar in terms of the height of these bars corresponding to what we saw previously in the notes when we actually plotted the probability mass function. So this confirms then when we simulate the sample, we get essentially what we would expect based upon what we know from the probability distribution. Okay, so then that concludes then this subsection of the notes.